Let me start my presentation. My presentation topic is Bridging Stress Degradation Model of UHP-FRC from Fitting Experimental and FEA Results. I'm Haruki Jimmy. I'm an undergraduate student of Hokkaido University. This is today's contents. First, background. UHP-FRC, Ultra High Performance Fiber Reinforced Concrete, is a cement-based composite material, strength with fibers. Due to its excellent mechanical properties, including a more than 130 MPa of compressive strength and a more than 9 MPa of tensile strength, the bridging stress degradation model represents the reduction of transverse stress under fatigue loads. It has still not been available for the UHP-FRC so far. However, this model is a necessary preparation for modeling the fatigue performance of UHP-FRC structures. Therefore, the purpose of this research is to obtain the bridging stress degradation model of UHP-FRC under cyclic growth through fitting experimental results and finite element analysis results of a UHP-FRC beam subjected to a 4-point fatigue bending load. Second, experiment. Based on the Japanese industrial standard, the experiments of 4-point bending static test are conducted with a load speed of 0.1 mm per minute. 5 specimens are conducted. In the 4-point bending fatigue test, the load level are calculated based on the load capacity of static test. In this study, 3 load level ratios 0.2 to 0.95, 0.2 to 0.9, 0.2 to 0.85 with respect to the static load capacity are employed for the fatigue test. Load frequency is 3 Hz. 12 specimens are conducted. Figure 4 shows dimensions of specimen. Third method. Step 1. Conduct finite element analysis of a UHP-FRC beam subjected to a 4-point fatigue bending load. Step 2. Assume a bridging stress degradation model of UHP-FRC under cyclic growth. Step 3. Compare experimental results with FEA results. Step 4. Change the degradation model, repeat 1 through 3 until FEA result fit with experimental results. A nonlinear FEM software, MSC Mark, is used for the analysis. Half models are used for the analysis of static test and fatigue test. Blue arrow shows support points. They are fixed displacement for Y and Z directions. Red arrow shows fixed displacement for X direction. Yellow arrow shows point load. The load is calculated by load capacity multiplied by stress level. In this analysis, 0.95, 0.9, 0.85, and 0.75 are used as stress level. Dimension of steel plate and UHP-FRC shows below. Steel plate are used as loading plate. Poisson's ratios and Young's modulus of steel are 0.3 and 200 GPa respectively. Poisson's ratios of UHP-FRC is 0.22. Material properties are determined by trials of epsilon CR, epsilon U, sigma CR, sigma U, with analysis until the FEM result fit with the experimental results. Bridging stress degradation model is shown in below. N is number of cycles. A0 and A1 are coefficients. Epsilon T is strain of tension strength. Sigma N is stress when N cycles. Sigma 1 is stress when fast cycles. FEA is conducted until fit to the result of experiment. Fourth result. Average load capacity of experiment and load capacity of analysis are 7.4688 kN and 7.65 kN respectively. Load capacity of FEA is 2.43% larger than that of experiment. Evolution of mid-span deflection from analysis and experiment are shown in Figure 7. Load displacement curve of FEA fit to that of experiment. In static analysis, the calculation stops at the load capacity due to convergence difficulties. This may be induced by the widely distributed crack elements in terms of softening behavior, it will be tried to obtain from now on. This is a result of FEM, when coefficient of bridging stress degradation model A1 and A0 and 5 and 0.015 respectively. The fatigue stress level to fatigue life relations acceleration is shown in above figure 8. S is defined as a ratio of the maximum flexure strength to the static flexure strength. Both analytical and experimental results are shown in figure 9. Evaluation of mid-span deflection from analysis are shown in figure 9 for 4 different fatigue load levels. It is found that the evolution of mid-span deflection depends on number of loading cycles and the fatigue stress level. When the stress level decreases, the number of cycles to failure increases as the mid-span deflection at the final failure reduced. Strain distribution is shown in figure 10. The gray area represents the cracked elements. Even though there is almost no propagation of the cracked range, the maximum strain increased by 1.73 times from first cycle to just before failure. It shows that repeated load fatigues the material and makes strain bigger, but UHPFC can still sustain. It is because the cracking strength and strain are much smaller than tensile strength and corresponding strain, respectively, due to the existence of strain handling domain. This proves that UHPFC has high durability even after the crack indentations. Coefficient of bridging stress degradation model of UHPFC, PVA-ECC, PE-ECC, and normal concrete is shown in Table 4. UHP-FRC has higher durability than other cement-based materials. Fifth, conclusion and future work. Conclusion. Material properties of UHP-FRC obtained from fitting experiment result of static test and FEM result of static test. Bridging stress degradation model of UHP-FRC and fatigue test was assumed. FEA was conducted and the result of FEA fitted to experiment results. UHP-FRC has higher durability than PVA-ECC, PE-ECC, and concrete. Future work. Try to get stress softening curve in static test. Change coefficient A0 and A1 to obtain upper and lower limits of degradation speed. Thank you for your kind attention.